Hello.
Hello. So can you hear me?
I cannot hear you, Samra. Just a second. Let me see what is the. Hello.
Hello, sir. Can you hear me? Hello.
Yes, Samra, can you hear me? Yes,
Hello.
Samra, can you hear me?
Hello, sir. Yes, I can hear you.
Okay, okay, good. I think earlier I was not audible.
Yes, sir.
Okay, good. So, yesterday I have shared you some more material on some diagnostic techniques, immunological as well as radioisotopic. Okay,
Yes, sir.
we
Yes, sir.
will discuss that part today.
Okay, sir.
So, I'm just sharing the slide. So today we will discuss about radioisotopes. Is it visible to you?
Yes, sir.
And I hope visibility is good. And just let me know when the slides are, if the slides are not moving.
Okay, sir.
Okay. So I hope, do you know some idea you have about radioisotopes?
Yes, sir.
So what is an isotope?
Sir, isotopes are the we can say that they have the elements that have the same atomic number but different mass number.
Okay, very good. So how come it is possible that an element can have same atomic number and different mass number? So what is the relation between mass number and atomic number?
Mm.
So what do you mean by atomic number?
Sir, atomic number means the number of electrons.
No, 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 no. Atomic number
No,
means the
sir.
number of
Number
protons.
of protons. Okay.
Number of protons. Okay. And what do you mean by mass number?
So they are protons plus neutrons mass number.
Protons plus neutron. Very good. So mass of proton plus mass of neutron.
Neutrons.
And like ideally or usually, what is the mass number? Is it equal to atomic number, lesser than atomic number, or greater than atomic number?
So it's greater than atomic number.
Okay. But usually it is mass
Sir,
number of carbon
12.
is 12. Okay.
12. Yes, sir.
Okay, so this is the most stable element or isotope of carbon. Then we have other carbon also, in which the mass number is 13. We call it carbon 13. And also
Okay.
in which the mass number is 14. We call it carbon 14.
Yes, sir.
So that means what has changed? Is it the number of protons has changed or the number of neutron has changed?
So
In
the
case,
number of neutrons has changed.
okay, now if the number of proton changes from 6 to 7, then what will happen?
So the atomic number will be changed.
Atomic number is, suppose it is carbon is 6.
Mm-hmm.
Now I say that it is 7 now. Now what is that? Is it carbon or something else?
It will be something else.
Okay, very good. So it is something. So atomic number decides that what will be the element,
Yes, sir.
and the mass number is a sum of protons and neutrons. So the number
Yes,
of
sir.
neutrons, it may be in ideal condition for the most stable element. Atom number of neutron is equal to number of protons. But what happens in some of the elements in nature, the number of neutron is higher as compared to the number of proton.
Protons.
So these elements which are having same atomic number but different mass number are known as isotopes. Very good.
Isotopes.
I hope you got the idea.
Yes, sir.
Okay. So like they are having same atomic number but they have different
Different mass number.
atomic mass. Okay. Right.
Mm-hmm.
So
Yes, sir.
what is the role of electron here? Does it play some role here? What is the role of electron in an atom? What is the role of electron? We are talking about proton, we are talking about neutron, but what is the role of electrons here? Do we need electrons?
Sir, electrons are similar, are same in number as of protons,
Okay,
and we decides the element by counting the number of electrons.
okay, okay. Actually, we do not decide the element by the number of electrons, but it is by the number of proton. One thing, right?
Okay, okay, sir.
Second thing is that why we have electrons, because we know that the atom is a electrically neutral moiety.
Mm-hmm.
Atom is
Yes,
an
sir.
electrically
Electrically neutral.
neutral moiety. So if we have protons, then we need to have electrons.
Hmm.
Okay,
To balance it out. Okay, sir.
to balance it, and the number of electron is always equal to the
Number
number
of
of
protons.
protons, because whatever, like suppose if we have 6 plus in carbon, then we'll have 6 electron which will be say neutralized.
Hmm.
Okay,
Okay, sir. Okay, sir.
good. Now when we come to isotopes, now why there is increase in number of neutrons, like what happens in some of the elements, particularly with higher atomic number, the mass is not exactly the double. That means equal to the possibly that the mass of proton is equal to mass of neutron. So if carbon is having 6 proton and it is having 6 neutron, then the mass will be 12,
12.
right? Mass
Yes,
will
sir.
be 12. But
12.
if carbon is having one extra neutron, then mass will be 13, and
Hmm.
two extra neutron, the mass will be 14.
14. Okay,
Okay.
sir. Okay,
Now,
sir.
in nature, it is there that we have elements in which mass number is exactly double the number of double the atomic number. That is, the neutrons are exactly equal to the number of protons.
Protons.
Right? But
Yes,
in
sir.
some elements of same atomic number may have different mass number, and usually atoms these elements are unstable. These elements are unstable. The
Unstable.
most, like you must have heard about a concept called natural abundance. Have you heard about the word natural abundance? Now we have three isotopes of carbon:
Hmm.
carbon 12, carbon 13,
And
and
carbon
carbon
14.
14. Which element is having the highest natural abundance?
Sir, carbon 12.
Carbon 12. Very good. Why?
Hmm. Sir, because it is the most stable one.
It is the most stable one. So the other elements, they are unstable. So unstable
Hmm.
means they will try to convert itself either in
Into carbon
carbon
12.
or to some other element also.
Okay,
Sometimes
sir.
they can be converted in other element as well. So if an unstable isotope means which is having, in which the number of protons are more than the
Neutrons.
number of neutrons are more than the number of protons. This is
Protons.
stable isotope. And if that unstable isotope, in the process of gaining stability, if it radiates energy, because proton is also energy, neutron is also energy, electron is also energy, right? So because atom is a combination of different energies. So if the energy of neutron is somehow shed by the atom and it is converted in a stable atom, and if the energy is shed in form of radiation, then these kind of isotopes are called radioactive.
Radioactive.
Okay, you got the idea?
Yes, sir.
Radioactive isotope. Like you see here, like for hydrogen, we have 1H1, 1H2, and 1H3. For carbon,
Hmm.
we have carbon 12, carbon 13, carbon 14. For phosphorus, we have phosphorus 31, 32. Then for like iodine, we have iodine 131, 137, right? So
Right, sir.
these are the different isotopes which are used in biology. Okay. So if an isotope is radiating out energy to gain stability, then this concept is called radioisotope.
Radioactive.
These are called radioisotopes, and this nature is called radioactivity. The nature is called radioactivity.
Radioactivity.
Okay, and there is no thumb rule that which element will be radioactive, but generally the elements which are having higher mass number as compared to the atomic number, they
Atomic number.
tend to become
Radioactive.
radioactive. So we have a concept called radioactive decay. Decay means the neutron need to be shed. Now, if the neutron is shedding itself, then it can shed in form of, like, energy is released in form of radiation. So when the energy is lost, we say it is a decay. And when the energy is lost in form of radiation, then it is called radioactive.
Radioactive decay. Decay.
So it's a process in which an unstable atomic nucleus loses energy by emitting ionizing particles and radiation. It may be particle, it may be radiation. This
Okay.
decay or loss of energy result in an atom of one type called the parent nuclei transforming into an atom of another type that is called daughter
Got
nuclei.
it.
Okay.
Okay, sir.
Now, radioactive decay or radioactivity, it may be either spontaneous, like you must be knowing that what Dr. Henry Becquerel discovered and what Madame Pierre Curie discovered. These were the cases of spontaneous and natural radioactivity.
Yes, sir.
Activity. It was not induced. So we say a spontaneous emission of radiation from a nucleus. So nuclear decay or radioactivity is the spontaneous emission of radiation from a nucleus. Okay.
Okay, sir.
Then, like radiation or radioactivity was later shown to be separate by electric field by of three different types. So either there may be a decay of an alpha particle, or which is a helium nucleus He2 plus emitted as alpha particle, then beta particle and electron emitted from the nucleus, and it is a like negatively charged particle, and gamma radiation where there is no particle, there is no change in the like atomic or mass number, but yes, there is release of energy in form of gamma radiation. Okay.
Okay, sir.
What happens in case of alpha emission? There is like emission of a helium molecule. Is a helium atom. Okay.
Yes, sir.
See, by emission of helium, or that is called alpha particle. Like you see in this case here, we have thorium, uranium. You must be knowing that uranium was the first uh, like atom which was discovered, which was like
Radioactive.
radioactive.
Yes, sir.
And you see the number of ratio of neutron to proton. Ideally, it should be 184 because atomic number is 92. Mass number here it is 238. Ideally, the mass number should be how much? 184.
184. Yes, sir.
But it is having it is 238. That means there are quite a good number of like the it is uh, like you say that it is like good number of extra neutrons are there.
Extra. Yes, sir. Yes,
Okay,
sir.
so now like uranium is naturally it is converted in thorium, which is having like atomic number
90.
90 and mass number is 234. But
34.
again, thorium is also not stable. It again decay and then give rise to other elements. Okay.
Okay, sir.
So what happens actually in nature that these radioactive elements they keep on decaying themselves so that like ultimately the energy is lost and they are converted in some stable elements, right? So that's why you will find that in nature the most stable elements are those which are having mass number exactly double to atomic number. Okay.
Okay, sir.
We have beta emission. So most of the radioisotopes commonly emitting biochemistry are beta emitters. The beta particle is uh, of two types. One is electron. We simply release electron that is called beta shown by sign beta minus. So decomposition of neutron to proton. Like if a neutron is converted in proton, because here there is no change in mass. There is only change in what? Charge.
Charge. Yes, sir.
Neutron was neutral. It is converted in a proton which is positively charged, and there is
Positive.
no change in the
The
no change in the
mass number.
mass. Okay,
Yes,
so
sir.
the nucleus ejects electron as beta particle and retain its proton. Okay, then another case is like you see, like this. This is you see here when carbon 14 is converted in nitrogen.
Nitrogen 14.
So it was 14. So simply one neutron is converting into what? Into proton.
Into a proton. Yes, sir.
Into a proton, and then you are having this seven number of
Nitrogen.
nitrogen, and it convert into nitrogen. Then we have the positron emission. So conversion of proton into neutron, right? So a proton means a positively charged particle is converted into a neutron.
Neutron.
No change in the uh, like mass will be same because there is no change in the mass, but only there is change in the there is only change in the atomic number. Like
Atomic number.
proton atomic number is reduced. Like it was in zinc, it was 30. Now
30.
it convert to copper.
Copper.
Okay. By removal of a positron, that is
Positron.
positively charged beta particle. So beta particle may be negatively charged. Beta particle means massless particle. Beta particle
Hmm.
means massless
Massless particle.
particle. If it is if it is negatively charged, then sometimes we call it electron because electrons are massless, negatively charged particle. Or if it is having positive charge, again massless, then it is called positron. Okay.
Okay.
Then we have gamma radiation. So a few radioisotopes of biochemical significance are gamma emitted. So gamma emission causes no change in the mass number or atomic number, right?
Yes, sir.
Gamma emission is often a secondary process occurring after initial decay of alpha or beta emission. Surplus energy is emitted as gamma radiation. Okay. Now you see
Yes,
here,
sir.
this is xenon. It is 131 54. It is converted into, again, there is no change in the mass number or atomic number. So atom is same, but we got gamma radiation is emitted. Okay.
Emitted. Okay, sir.
Okay. Then like alpha particle and gamma rays are they are ionizing radiations. So possibly you know what you mean by ionizing radiations. Ionizing radiation means like when if this energy, if it is deposited in a molecule, in a tissue or whatever, like in an atom, it can like like convert it, that molecule, in an ion, that
And yes,
molecule
sir.
ion. So these radiations are ionizing radiation, and that's why these radiations are very harmful for biological systems. So why these are harmful? Because if we have our stable molecule like DNA or protein, if we expose them to these ionizing radiations, then what happens that these ionizing radiations, due to these ionizing radiation, the structure of the nucleic acid or protein may change, and that change in structure of nucleic acid or protein, it may induce, like particularly in the structure of, like the protein may become non-functional, and if it is DNA, then it may lead to mutations. Okay.
Okay, sir.
Harmful. So these, we have to avoid these ionizing radiations. Okay. So a
Yes, sir.
general name for ionizing radiation is a general name for the high energy radiation of all kinds, such as alpha particle, beta particle, gamma rays, X-rays, or cosmic rays. Okay. So which can induce ionization. Ionization means how the ionization will be induced in a atom or a molecule by
Sir, when
emission, by ejection of
of
electrons.
electrons.
So with that energy, the electrons will be ejected, and if the electrons will be ejected, then the molecule will be converted in a ion.
Ion.
Because ideally, like an atom is a neutral moiety, then the molecule is also a neutral moiety. So if
Yes,
an
sir.
atom is converted into ion, it is unstable. If a molecule is converted in if the molecule is also converted in ion, then this also it is again unstable. Okay.
Unstable. Yes, sir.
So we have a concept called radioactivity half-life. Half-life means, like possibly you might have heard about the concept of carbon dating.
Yes, sir.
Heard about that? Some idea what is that? Carbon dating? Yes, Samra?
Sir, by carbon dating would remind the age of the
Yes,
some.
yes. So we can determine the age of a fossil.
Yes, sir.
Age of a fossil. You know what is a fossil?
Yes, sir.
Yeah, what is that?
Sir, fossil is something that is just preserved in
Mm-hmm.
its natural form.
Mm-hmm. Now suppose I have a stone, and that stone is preserved in its natural form. Is it? Can we call it fossil?
No, sir.
Okay, then.
So in fossils, we considered it of being the living things.
Yes, good. So fossils are living things, living organisms,
Mm-hmm.
which they have lived sometime on this earth,
Yes, sir.
but their structure is preserved, like their skeleton is preserved or their shape is preserved somehow. How somehow? Like particularly we get fossils mostly like you'll find that suppose we have a large forest and then we have a say volcanic eruptions. In that volcanic eruptions, some of the plants they will be preserved as such. They will not be burnt like due to the like like lot of coming lava, and that lava is putting like it is preserving things.
Yes, sir.
One way of fossilization. Another way may be like in the Antarctica region where everything is cold. So the
Yes, sir.
biological form like bacteria or organism may be fossilizing. Okay.
Okay, sir.
So if we want to know the age of that fossil, then we have developed a concept called
Carbon dating.
carbon dating based on the concept of half-life of the element. Like so, what happens actually? Half-life means that like how many years ago, like half-life means like the rate of nuclear decay at the time required for one half of the radioactive sample to decay. Let's just try to understand. Suppose today I have say X amount of radioactive material present in an organism, in a fossil. Now I can
Okay, sir.
find out that what was the like 2x material available when it was 3x, 4x, 5x like this, right? You got it?
Yes, sir.
So this way we can find out that what will be the like at what time this organism has lived on this planet. Okay.
Okay,
So
sir.
so many isotopes have been used. Like you see for carbon dating, if you remember, carbon dating is largely used for assessment of age of all organisms, like for plants, animals. Possibly, you know that the age of like dinosaurs was assessed using carbon dating
Yes, sir.
because you see the half life. Half life is 5,570 years, right?
Yes, sir.
5,570 years. Now, if we talk about the civilization today, if we talk about the civilization today, how old the civilization is? Do you have some idea how old the civilizations are? Like you might have heard about, I'll give you example. You might have heard about that the oldest civilization is said to be the Harappa Valley civilization.
Yes, sir.
Now, what may be the age of Harappa Valley civilization?
Sir, it might be several thousand years back, but I don't know the exact value.
Yeah. Like like we have the concept of AD and BC.
Yes,
Now
sir.
we are in AD or BC?
Sir, we are in AD.
AD. What do you mean by AD?
It's like some after.
Okay, it is a Latin word called Anno
Yes,
Domini.
sir.
That means in the year of birth of my God. And this is like
Yes, sir.
the current AD system we are following. It is Christian era,
Yes,
right?
sir.
So Christian era started with the rebirth of Jesus Christ.
Jesus Christ. Yes, sir.
So that's why it was called AD. That is Anno Domini, which means in the year of birth of my God. Now, if you talk about Harappa civilization, the duration of Harappa civilization was around 4000 BC, 4000
Okay.
to 6000 BC. Now, BC means before Christ.
Before Christ. Yes, sir.
If it is was 4000 BC, then how many years from today? How many years ago from today? Yes, how many years from ago from today? So we can say that around 6000 years to around 8000 years.
Yes, sir.
6000 years to 8000
Six
years.
thousand years. Okay.
So if some, because it was a civilization, that means like human being was living in civilized manner. Possibly you know that we say na that is primitive man.
Yes, sir.
Primitive man was like staying in like forests, in caves, and
Yes, sir.
primitive man whenever man, like when the person was hungry, he used to hunt and eat. So this was primitive man. But when we talk about civilization, so civilized means when the human beings started staying in, say, colonies or villages, they made villages, they got settled, huh? They made
Yes, sir.
houses, they started practicing cultivation, they have a society, means they have certain norms of the society and like this. Okay, so
Okay,
this
sir.
concept, when this concept was given, we called them civilized, and these like inhabitants, they were called civilizations, right? Like
Yes, sir.
Harappa civilization, Egypt Valley civilization, Mesopotamia civilizations. They were all civilizations which has no, uh, like survived on this earth.
Yes, sir.
But yes, we said that the Harappa civilization was the oldest one. Okay,
Oldest one.
using carbon dating. Today also people are, and you know what was the area of Harappa civilization? Indus Valley civilization. Na? You know what was the area where it flourished?
Sir, it was somewhere around in Pakistan.
Yeah, yeah, it was in Indus Valley, and
Yes,
that
sir.
Indus Valley currently it is in Pakistan, but its area was today's India's Punjab,
Yes, sir.
part of Rajasthan, part of Haryana, and part of Uttar Pradesh.
Okay, sir.
And then it went up to the Lahore and then that area in
Hmm.
Pakistan. So
Yes,
it
sir.
was that area where this civilization has survived. And even today also, like archaeologists, they are doing excavation in Haryana, Punjab, Western UP or
Yes,
Rajasthan.
sir.
And whenever they find that, like during some kind of construction work, if they find that something is being taken out, they always record it and then try to find out that what actually it is. Okay, right?
Okay, sir. Yes, sir.
So so if today we find that some of the elements are like some of the fossils they found there, so they try to find out the age of those fossils. Okay, and that is
Yes, sir.
largely done using a
Carbon dating.
carbon dating. That is the concept is called carbon dating. Okay, but in
Hmm.
biology, like carbon 14 is not very suitable. Why not very suitable? Because it is having a very long half life.
Hmm.
Means if it is today, if it is say 100, it is 100. I think it is one scale is there. So it's a 100 nanogram. Then it will take 5,570 years for it to become 50 nanogram, right?
Hmm. Hmm.
So, but for biological process, we require elements which are having shorter half
Short
life.
half-life. Yes, sir.
Generally, we use phosphorus. Now, see, the half life is
40 days.
14 days. It's very easy. If I give radioactive phosphorus to some organism, then I can trace that how the organism is like, how the metabolites are being converted.
Hmm.
Then
Yes, sir.
you see, iodine is very routinely used, which is having a half life of 60 days.
60 days.
And then you have the iodine 125 60 days and iodine 125 8 days. So these are
Mm-hmm.
very widely used in biology. So mostly phosphorus we use,
Mm-hmm.
iodine. Then you see uranium. See,
Yes,
the
sir.
half life is above billion years.
Billion years. Yes, sir.
But can you use it in biology? You cannot use it in
Yes,
biology
sir.
because we are not going
Hmm.
to
Live for
live
billion
for that
years.
time. Okay.
Yes, sir. Yes, sir.
So the SI unit of radioactive decay, the phenomena of natural and artificial radioactivity is backward. It is to honor the discoverer
The
of
inventor. Yes, sir.
radioactivity, Henry Becquerel. Okay.
Okay,
And
sir.
one Becquerel is defined as one transformation per second.
Per second.
Okay.
Yes, sir.
Then, like it is again Becquerel one disintegration per second. Then we got, Madame Pierre Curie. She
Yes,
also
sir.
has remarkable work in
Mm-hmm.
radioactivity. She got Nobel Prize. So to
Yes, sir.
honor her, we have Curie also. Okay,
Mm-hmm.
so one Curie is equal to 3.7 into 10 to the power minus 10 to
Mm-hmm.
the power 10 Becquerel.
10 backward.
That means
Mm-hmm.
Becquerel is a bigger unit, Curie is a
Mm-hmm.
smaller
Smaller
unit.
unit.
Okay,
Yes, sir.
okay. So how to measure the radioactivity? So for that, for measurement of radioactivity, we have different counters. We can call them counters.
Hmm.
Counters means counting of radioactivity.
Yes, sir.
We have, I think you might have heard about GM counters,
Yes,
Giger-Muller
sir.
counter. Then we have
Yes, sir.
scintillation counters. And the third method of measuring radioactivity is autoradiography or say photographic exposure. Okay. So generally in lab we use all the three methods. So GM counter, that is otherwise called as Giger-Muller counter, it is one of the common device to detect radiation, particularly the beta particles. The Geiger counter is simply an argon-filled tube with two electrodes. So when radiation, whatever whether beta or gamma radiation, collide with the gas atoms, the gas is ionized and there is
Hmm.
ejection of electrons. Now these
Yes, sir.
ejected electrons they feed to a circuit and there is generation of a current.
Current.
So how much current is generated is directly proportional to the, I just tell you this little
Ionization.
time, like how much current is produced, it is directly proportional to the amount of ionization. And the
Yes, sir.
amount of ionization will be directly proportional to the amount of radiation.
Radiation.
So
Yes,
like
sir.
it's very simple instrumental design. We have a glass tube and then we have it is filled with argon tube and then we have two electrodes. The wall is cathode and the in between we
Electron.
have anode because anode
Hmm.
is positively charged, so it is a
Hmm.
collector of electrons. And this is a thin window by which like dust particle or anything cannot enter, but only radiation can enter.
Hmm. Okay, sir.
Now, radiation, like suppose if we say that some source is having radiation, that source is brought near to the GM counter, and then whatever electrons are liberated, these electrons are taken by these node and they are given to a circuit, right? So when they are given
Okay,
to
sir.
a circuit, then current will be generated. But to accelerate those electrons, we need to apply very high voltage because we do not know. Like suppose if one electron is given, so one electron is nothing. It
Yes, sir.
won't be able to detect it.
Okay, sir.
So to generate, like to accelerate these electrons so that they can easily reach to the circuit, we apply very high voltage.
Voltage.
In we say that giga range. What we call it? Giga range.
Giga range.
So that giga range is called say around 2000 volts. Around 2000 volts.
Hmm.
So that's why
Yes,
it
sir.
is called Giger. Giger means giga range.
Giga range. Okay, sir.
Giger Muller counter. Okay. So these are some of these are one of the most widely used counter which is used in the biology. Okay.
Okay, sir.
Then proportional counters we are not using, so I'll just skip that. Then another one that is because Geiger-Muller counter they are called gas counters, right?
Hmm.
So if
Yes, sir.
radiation is available in air, it can be measured using the Geiger-Muller counter, right?
Yes, sir.
Now, uh, but mostly you see that in biology, either the radioactive material is inside a tissue or
Hmm.
it is inside a fluid,
Yes, sir.
right? Means it is
Yes, sir.
in a liquid media. So
Yes,
if
sir.
it is a liquid media, then how to like how to detect it, how to go for it. Okay. So how
Yes,
to
sir.
detect it? So for that we designed what? We designed scintillation counter.
Scintillation counter.
Scintillation. Scintillation means flash of light.
Flat. Yes, sir.
Flash of light. So for this, what we do actually, this is done in a solvent. So in the solvent, what we have, because this is one of the most widely used radiation counter in biology. Why it is widely used? Because we have